What you think about how they combine is using the standing wave theory. So we talked about the wave, and in the at the lowest energy level, it never passes through zero. We call this the first harmonic. And then this is second harmonic. Third harmonic. And then the fourth harmonic. Right, and so each one of these waves, that's how we use that to describe the orbitals. And we talked about the p orbital itself, right? Being, we know that an orbital is not real. It's an equation or the graph of the equation that delineates the path of an electron around a nucleus. So the p orbital itself, with it being an equation, has a node in the middle between the lobes, and that means that the sign is different in one lobe compared to the other, right? It'd be plus or minus. And shaded doesn't mean plus, right? That's just a convention to shade the top lobe, but we could just as easily shade the bottom lobe and leave the top lobe unshaded. That doesn't change anything. But what matters is over here, right? So we have these 4 p orbitals and these 4 molecular orbitals. You can see that there are 4 different combinations of p orbitals, and as energy increases and the frequency of the wave increases, the orbitals change, right? So in the first harmonic, right, all the orbitals have the same sign. Second harmonic, which is up top, in the second harmonic, the wave passes through zero once, so there's a sign change for your orbitals. Third harmonic, which is the next energy level, and energy is increasing now, not decreasing. So as we go from bottom to top, the energy is increasing. Third harmonic, this is going to have 2 nodes. Now the wave is going to pass through zero twice, and you have to shade your orbitals accordingly. Let me fix this one. It's like a Charlie Brown load. So you shade your orbitals accordingly, right? So here we're shaded. The first orbital is shaded, and then when the wave passes through zero, the signs change of the other 2 orbitals, and then when it passes back through zero, the sign changes back. Right, so that's the third harmonic, and then the fourth harmonic. And the fourth harmonic, right, the fourth harmonic, which is the very top, is alternating. Because there are 3 nodes with 3 places where the wave passes through zero, so the signs of your orbitals are going to alternate. All right, any questions about that part? This, the reason this is important is because it's these molecular orbital diagrams that help us to understand the reactivity of 4-pi systems or 6-pi systems or 8-pi systems or even 2-pi systems. Even though 2-pi systems aren't conjugated, we can still construct a molecular orbital diagram for a 2-pi system. Let's do that real quick, and then we're going to talk about another aspect of the 4+2 cycloaddition, which is the transition state and what it looks like. All right, any questions about anything? So for a 2-pi, we can draw the MO diagram. Right, if this is my alkene, it has 2 p orbitals. To make that pi bond, each p orbital has 1 electron in it. So because of that, if I have 2 atomic orbitals, what does that mean for the number of molecular orbitals? How many different ways can those p orbitals combine? That's the way to think about it. So how many molecular orbitals should I expect if I take two atomic orbitals and add them together? Right, it's always the number of atomic orbitals. So if I have two atomic orbitals, I can expect two molecular orbitals where these can combine in two different ways, right? What about the wave part of this, right? What about the wave part? How does the energy is increasing in this direction? How does the wave look here? If this is the first harmonic, how does the wave look? Does it pass through zero? Does it not ever pass through zero? What did we say about the wave, the idea of the standing wave with the 4-pi system? Because that concept is not going to change, regardless of if it's a 4-pi, 2-pi, 10-pi, it doesn't matter.
I'm just trying to answer the question. I don't know if it's right all the way, but I remember last class, you said when it was going through zero, it created I think 4 different waves, if I'm not mistaken.
Yep, okay, great. So that was with a 4-pi system. You have 4 molecular orbitals. So you have 4 different waves, right? 4 different types of waves, to put it that way. We'll say it that way. All right. So the wave had basically 4 different iterations, right? Or 4 different frequencies. And the first harmonic, that's the lowest energy level. And then the frequency increased going to the second harmonic. So it passes through zero once. Third harmonic passes twice. Fourth harmonic, it passed through. Let me make sure that's visible 3 times. So you got 3 nodes. So down here, you don't expect anything different, right? The same concept. First harmonic, the wave is not going to pass through zero. Second harmonic, the wave is going to pass through zero once. All right, now let's think about that in terms of orbital shading, right? The signs of the orbitals. First harmonic, what do you expect? If those p orbitals, if the top lobes are shaded, what do you expect for the wave itself or for the orbitals themselves? Anybody? What happened up here? Did the signs of the orbitals change at all in the first harmonic?
No.
No. So here with a 2-pi system, that's not going to change. Right. So the orbitals, both of those are going to be shaded. What's going to happen when that wave passes through zero? If this is shaded.
Wouldn't it continue to go below zero because it's negative?
Yes.
Or no? Oh, okay.
Yes. So this is going to be shaded like that. So in other words, there's going to be a sign change. Anytime the wave passes through zero, if we think about it, this is the positive side of the coordinate, and then this is the negative side. So you'll see a sign change, right? And then what about my electrons? Because this is a 2-pi system. All right, it's a 2-pi system. So that means there are 2-pi electrons. Where do we put them? If you remember from CHEM, how do you fill up orbitals that have the same energy, right?
Generate. So you'll fill them up one at a time. With p orbitals, there are 3 levels and 2 electrons in each one.
Right. So in this case, I'm going to put both electrons in the lowest energy level. So don't think about it like 3p where you put one in each before you put two in any. I agree with that. But for this particular case, the lower level orbitals have to get filled up before you go to the next energy level. That's the idea I'm getting at. So that's like going from 1s to 2s, right? If you have a 1s, 2s electron configuration, something like that, you're going to fill up the 1s before you touch the 2s, right? And since the top orbital is higher in energy, you're not going to put an electron there before you fill up the bottom lower energy level orbitals, right? So whenever you have a molecular orbital diagram, no matter whether it's a 2 pi, 4 pi, 6 pi, doesn't matter. You always want to fill up each molecular orbital first, the lower level, and then you move to the next. If you got more electrons, then you'll fill that, and you keep going in that direction. Because one of the things that with these molecular orbital diagrams, if I were to do this instead, right, that would mean that now I'm in the excited state. And that's not possible unless you have some external radiation, like some UV light or something like that. So in general, you're going to fill this up first before you touch the other one. Does that make sense?
So you're talking about like, because, okay, so I know when we write out the electron configuration, they have to be with P. What you're saying, when we fill the orbital in the diagram, even with P, we fill the bottom level first, this, the bottom level?
Because, and the reason for that is, that's a great question. And I like how you're thinking about that. The reason for it is that these are molecular orbitals. They're not atomic orbitals. If they were atomic orbitals, then you'll have px, py, and pz, and then you'll put one electron in px, then one in py, and then leave pz empty if you only had 2 electrons, right? But when you take those atomic orbitals and that's the whole concept of molecular orbital theory, that you take the atomic orbitals and you combine them to get molecular orbitals. So since I started with 2 atomic orbitals and I added them together, they can combine 2 different ways. So I get 2 molecular orbitals. Hence, I have a molecular orbital here. This is one, and then this is the other, right? So when you fill up the orbitals with electrons, you're basically filling up each energy level with 2 electrons before you put one in any of them, right? Does that make sense?
Yeah, it does. And then I just have one question. So you know how when we do the molecular orbital diagrams, we would do the sigma and then pi and then anti-bonding and bonding. We're not doing any of that for
not so not in the sense of, so what you're thinking about is bonding between 2 different atoms. And what we're doing here is constructing MO diagrams. So, but you do have a bonding and non-bonding concept here. So you're right? So here, this is bonding because this is where the electrons are. That's a great question. And it leads right into what I was getting ready to talk about. This is anti-bonding. So this is pi and this is pi star. Right? When you do this for sigma bonds, it's a little bit different, but it's the same idea, right? So you have a sigma and sigma star, but this is here we're talking about pi bonds, so it's a little bit different, but the same concept, right? So pi star bonding because of the electrons are there, anti-bonding, and then there's another idea that I want to bring out, and then we're going to talk about this transition state. And that's the idea of what we call the HOMO and the LUMO. Right? So the HOMO is, I need more room. I'll just write it down here. It's the highest occupied molecular orbital. And then the LUMO is the lowest unoccupied molecular orbital. Every MO diagram has a HOMO and a LUMO. And the LUMO is typically going to be one of your anti-bonding orbitals. And then the HOMO is going to be one of your bonding orbitals, right? So if we go back up to the 4-pi system, right? This is the HOMO because it's the highest in energy. It's occupied, meaning it has electrons, and it's the highest, so it's the highest occupied molecular orbital. And then right above it would be the LUMO. And when we are talking about molecular orbital theory, the HOMO and the LUMO govern the reactivity, right? They govern all reactivity of molecules that when we're looking at MO theory and how specific types of molecules react, the HOMO is always some HOMO-LUMO interaction that controls reactivity. Let me put that here. Right, so for pi systems like these, any reaction that happens on these systems is going to happen either through the HOMO or the LUMO. All right. Any questions about that? Any questions about the acronym? Right.
Well,
Go ahead.
when you say highest, it's like highest occupied molecular orbital, right? So
Yeah, highest in energy, but it's not just highest; it's highest occupied. So it's got to have electrons in it too, because obviously the other two orbitals are higher in energy, but they're empty. So that's why the occupied part matters. So it's the highest occupied molecular orbital, which is true, right? It's in the second energy level, not in the first. So that's a higher energy level, and it has electrons in it. And then the LUMO is empty. That's what unoccupied means. It has no electrons.
okay, yeah, that makes sense.
Mm-hmm. All right. So what does all this have to do with the 4+2 cycloaddition? Let's talk about it, and then we're going to do some examples. So when the 4+2 happens, this is always the case. Always the case. The HOMO of the diene overlaps with the LUMO of the dienophile. Right, and remember, anytime you make a bond between two atoms, it's the result of orbital overlap. Right, anytime. So if you watch that Deals All the video, you should be able, this should not be foreign to you. If you didn't watch it, then it's probably sounding like Chinese right now. Or if you haven't looked at this section in the book, which is in the syllabus, tells you what section to read. If you haven't done any of that, then yes, this is all Chinese right now. It's another language. But with my diene, right, the HOMO looks like this. This is my 4-pi HOMO. And then with my dienophile, let's just say it's this reaction right here. So this plain Jane, no substituents, plus that going to this. All right. This is a very powerful reaction, by the way, and very widely used for making these cyclohexane derivatives. Widely used. And you can control the stereochemistry, you can control the electronics, you can determine which end of the diene reacts with which end of the dienophile, all of that. So it's stereo controlled, and you can also assert some regio control, all of that. It's a very powerful reaction. And the reason is because it's so easy to control certain aspects of the reaction. All right, so here's my diene. And then this is my Diana file. And remember up here, this was the LUMO. So I'm gonna put the LUMO down here. And this is how these two interact. Now, the question is, which one of those two top lobes should be shaded and which one should be left unshaded? And if you answer that question, you gotta tell me why. And if you watch the video, you should be able to tell me why. But don't let the why part scare you away from trying to answer the question. Anybody?
I'm gonna guess one shaded on the top and one shaded on the bottom.
Yeah, I mean, it's going to be, this is what the LUMO looks like. So that's going to be the pattern either way, right? But the question is now, if I want to overlap, I got to overlap these orbitals. So I need these orbitals right here to overlap. And I need these orbitals right here to overlap so I can share electrons. The question now is, how do I want to shade those orbitals so that they overlap properly? And it's kind of well, I ain't gonna say it's a trick question because it's definitely in the video, but it's kind of a trick question, but I just want to see how you're thinking about this. Then keep in mind too, that orbitals are equations. And so if you add them together and they have the same sign, they're going to add and they're going to be complementary. If you add them together and they got different signs, then they're going to basically cancel one another out. So what do I need the sign of this top lobe to be if I wanted to overlap with this lobe right here?
Shaded on the top.
I needed to have the same sign. See, you didn't really have to guess, did you? Once you understood the idea behind orbital overlap, then it really wasn't a guess. Now you know. If I want orbitals to combine constructively, they have to have the same sign. So this is what we call constructive overlap. So the orbitals have to have the same sign. If they don't, then they're going to cancel. So we got to have the same sign for proper overlap. All right, so what about on the other side? Was that you, Danielle?
Yes.
Right. I know
It'll
your
be
voice. I
shaded
know
on.
your voice now, so don't feel bad if I call you out. I'm not really calling you out. Go ahead.
It's okay. It's gonna be shaded on the bottom.
Right here, right?
Yeah.
Because this is unshaded. And so in order for it to properly overlap, they got to both have the same sign, right? That's called it's constructive overlap. If they have opposite signs, they're going to cancel. That's destructive overlap. And you don't want that. If you're trying to make a bond, you want constructive overlap. So this is what the transition state of the Diels-Alder reaction looks like. And this is why it's stereospecific. Let me give you that, and then we'll move on to the next, start working through some of these problems for a few minutes. So if I have a diene like this and I have a cis dienophile that looks like this, right? When that diene comes in, there's no opportunity for those substituents on that cis double bond to rotate. There's no bond rotation, nothing. So that's why when you get the product, those two groups are still cis. It's because of the nature of the transition state, right? And if the diene came from the bottom, I'm gonna just put this here because it can, right? The diene came from here. Actually, let me do this. If it came from the bottom like this, then you get different the stereochemistry is going to be a little bit different. So if it came from the bottom, then you could say that these will be wedged like that. So you can actually favor one approach over the other. It's more complicated than just saying you can favor it. You need a catalyst, you need something that's going to direct the approach, so on and so forth. But you can favor one approach over the other. But the basic idea in the transition state is that the diene can either come from the top and interact with the lobes that way, or it can come from the bottom and interact with the lobes that way. But either way, you can have either approach unless there's some bias incorporated. And here there's none. So you'll get one of these two products or a mixture. All right. Questions? Any questions? All right, let's work through some problems down here, right? Again, it's asking to predict the products. We kind of have an idea of what the mechanism is because it never changes. It's always, and let's number these because I think that'll help us to keep track of our atoms. So this is 4, that's 5, that's 6. All right, so I'm going to attack here. That pi bond is coming here, and this pi bond is shifting that way. So in the product, I'm always going to get a 6-membered ring. Right, where's the pi bond going to be? Let me put the numbers back. 1, 2, 3, 4, 5, 6. Where's the new pi bond going to be?
On 5 and 6. Wait, I'm sorry, pi bond is going to be on 2 and 3.
Between 2 and 3, good. All right, good. And that never changes. So if that helps you to number the diene and dienophile, it helps you keep track, do it. Right, let's do the next one. 1, 2, 3, 4, 5, 6. Right, the arrows never change. This pi bond attacks to put a bond between 4 and 5. It makes this pi bond shift, and then you attack to put a bond between 1 and 6, and then it's going to cause this pi bond to shift here. It never changes. So my basic structure is always going to be a 6-membered ring, right? And then this is 1, 2, 3, 4, 5, 6. What's attached to 6? What do I need to put back from the starting material?
Bromine.
Bromine, right? I need to put that back in. I'm not going to define the stereochemistry because in this case, it's going to be racemic, right? Because there's no impediment to approach from the top or bottom. So it's going to be racemic anyway. So I'm just going to leave it as a straight line, not a wedge or a dash. What else do I need to put back in? What's on carbon 2?
The H3CO.
Yeah, so the
What's
methoxy.
the name of that?
That's a good question. It's a methoxy.
Okay, thank you.
It's OCH3. Anytime you see that, we call that a methoxy group. Good question. And I wrote this is just a convention, writing the CH3 backwards like that. It's just a convention. If it's on the left side, you write it like that. If it's on the right, you just write it as CH3. It doesn't change anything. It's just semantics. All right, so over here, I need to put that back. Put that back, boom. And then where's my double bond going? My new pi bond.
The second carbon or the second to third.
Right here. That's not going to change. If you got them numbered and you find your diene and your dienophile, that will not change. If you number the dienophile that way, 1, 2, 3, 4, like we have it here, the pi bond in the product is always going to be between 2 and 3. Doesn't change. What about the next one? What are we doing there? And all of these have to be done with heat. This is it's an endothermic reaction. So you got to heat it up to get it to go. That doesn't change. And I'll also I'm gonna go back to that previous example because there's another idea that I want to flesh out in that example. All right, so I'm going to get this always. This is 1, 2, 3, 4, 5, and 6. Over here, same thing. 1, 2, 3, 4, 5, and 6. And then on carbon 1, in the start material, I had a chlorine. So then put that back. I don't lose atoms. Atoms don't just disappear. And then where's the double bond, the new pi bond going to be?
The same as the last two.
The last two, between 2 and 3. And you can see that based on the arrows too. All right. Now, let me go back to this top example because this also that's another couple of pieces of information I want to give you in that top example. Right. So here, that methoxy is actually a donor. It's a electron donor. And then bromine, because of its electronegativity, even though it has a bunch of electrons around it, is an electron acceptor because, or we call it an electron withdrawing group. And then over here for donor, we just abbreviate that as DON for donor, right? So, but this is important because for your dienophile, if you add an electron withdrawing group, it's going to make it more reactive. Right, so if you add, what happens if you put an electron withdrawing group on there is the energy of the LUMO decreases, right? So it brings the HOMO and LUMO closer together in energy. That's why that makes it more reactive, right? And then if you add a donor to your dienophile, it does the same thing, but it's the opposite effect. A donor raises the energy of the HOMO. So either way, you're closing the gap between the HOMO and the LUMO. And anytime you can do that, you're going to increase the reaction rate. So donors increase the reactivity of the diene. So if electron withdrawing groups make the dienophile more reactive, donors make the diene more reactive. That's a common characteristic for the 4+2 cycloaddition. All right, and then let's do the last one here. All right, somebody help me with that. I'll put the numbers in, you can put the arrows in, and then we're going to draw the product.
So we're gonna put an arrow from 6 to 1.
Okay, you want to start there?
Yes.
And then so let's think this through though. The diene is normally considered the nucleophile. So you want to start here. You're right that 6 to 1, that arrow from 6 to 1 is going to happen, but that's not going to happen first because the electrons are typically coming from your diene to your dienophile. So the 4 to 5 arrow is going to happen first. But the 6 to 1 arrow is going to happen. I agree with that. I don't disagree. All right. What else? You're right.
I'm assuming we're gonna shift the double bond down to the second. Yeah.
Okay, let me ask you a question. That carbon 1, it has 2 hydrogens on it. How many bonds would it have to it if we didn't shift that bond between 2 and 3? But we made a bond with carbon 6 on the other side. If it had 2 hydrogens on it, right? Already. And I made a bond with carbon-6 from the other side, which is what that arrow is indicating. And I don't move the pi bond. How many bonds would carbon-1 have to it?
1, 2, 3, 4, 5.
Is that legal? Does that ever happen?
No.
Never happens. So that's why you shift the pi bond, right? Because you can't have 5 bonds to carbon-1. So when this pair of electrons comes in right here, it's going to force these that way, right? That's just, it has to happen like that, right? When these come here, it forces that pi bond between 5 and 6. It forces that out. All right, so let's think about the product. I'm gonna draw the back part first. So I'm gonna keep this. That doesn't change. But what does change? I have a new set of bonds here. All right, and this is 5 and 6. And this is 1, 2, 3, and 4. Anything different? Arrow wise, electron wise, did anything change other than what's attached to your diene?
No, not really. Maybe the one
one?
double bond
So
between the
where's my,
second and
okay, so we need to put that in, right?
yeah.
The point I'm trying to make is that the mechanism never changes. And if the mechanism doesn't change, then the products, the only thing that changes are the products, because the diene and dienophile are going to have different structures in different problems. But as far as the arrows are concerned and which bonds get made, which bonds get broken, that will not change ever for a 4+2, right? Now, if it's a different type of cycloaddition, and you're going to have different arrows, right? If it's a dipolar cycloaddition, you're going to have different arrows, different electrons moving. But if it's a 4+2 Diels-Alder, if you number your diene and dienophile, you can put that in the bank. If you're able to draw a 6-membered ring, you can put it in the bank. All right, let's look at, I'm gonna stop early today. Let's look at this next problem right here. All right, this is gives me a chance to introduce another idea with this reaction. All right, so this is my diene. This is the dienophile. Right, even though you got a conjugated system with pi bonds, right? That's not the diene, right? It's a different functional group. A diene means that it's 2 double bonds together. So don't confuse it. Even though you see a pi bond and then you see a pi bond between carbon and oxygen, that's not your diene, that's your dienophile. And it's the pi bond here that's going to react. Right? So the diene itself, the way it's drawn, the reaction can't take place. Can somebody tell me why? Somebody who watched that Diels-Alder video, the first one. Tell me why the diene in its current state can't react.
It doesn't have enough electrons.
It's got plenty. It's got plenty. It's got four pi electrons, 2 in each pi bond. It's not electronic. It's more structural than it is electronic.
Oh, right. It's got to be cis.
Good. The pi bonds have to be on the same side of the sigma bond. Right here, they're not. This is the sigma bond that connects your 2 pi bonds right here. And the 2 pi bonds have to be on the same side of that sigma bond. So I'm gonna let me draw it this way. So it will be here, like this, here, like that. That's what that looks like if I just turned it. All I did was turn it 90 degrees. So the 2 pi bonds are, I could show you the actual orientation of it, right? So what I have to do is rotate around this bond, because right now, this is what we call S-trans, right? That means that the 2 pi bonds are on opposite sides of the sigma bond. that connects them. Right? In order for this thing to react, it needs to be what we call S-cis. Like that. And all I'm doing is rotating around that sigma bond that's connecting those two pi bonds. So this is S-cis. If it's S-cis, then the orbital overlap that's needed can happen. If it's S-trans, it cannot. You can't react through S-trans. And this is why. So if this is my pi system and my p orbitals are here and here, and I'm trying to overlap that with a 2 pi system here, right? Can't do it. Can't overlap properly. So anytime you do a 4+2, and that's why you need that energy, because S-trans is really the preferred conformation. So that's why you need to warm this up, because you need the energy present to rotate around that sigma bond first, and then react that with this. And let's number it. 1, 2, 3, 4, 5, 6. What's the product look like? This won't change. So what does my product look like? Is it a 6-member ring?
Yes.
That'll never change. Where's the pi bond, the new pi bond in that product?
It's at the second carbon.
Here?
Yeah.
What's attached to carbon 1 and 4?
CH3.
Oh, CH3s that were on them, and the star material. What's on carbon 6?
A double bonded oxygen.
Yeah, so the aldehyde is here. Right, and it's still 1, that's still 4, this is still 6. All right, we got to stop here because I got to charge my iPad for the next class. So let me stop recording and sharing.